In the distant outskirts of our solar system, far beyond Neptune's pathway, hidden and ancient worlds dwell in perpetual shadow. Pluto, long dismissed as a simple frozen sphere, surprised us with vast icy volcanoes and a sky that gradually fades away. Nearby rests a smaller celestial body called Oricoth, its reddish, flattened snowman shape guarding secrets about how planets first emerged. What mysteries are sealed beneath Pluto's frozen shell? What strange forces shaped Orica's unusual silhouette in the quiet void? And might elusive life persist within Pluto's concealed ocean? As we embark on this voyage, we uncover recent revelations about Pluto and Oricoth, two remote enigmas clinging to the solar system's edge. What exactly is Pluto's spacecraft? When NASA's New Horizons spacecraft swept past Pluto in July of 2015, it upended everything we believed about this far-off dwarf planet. Rather than a silent, icy rock, Pluto revealed a landscape of richness and surprising youth. Among the most remarkable findings was an intricate network of gigantic cryovolcanoes, mountains of ice unlike any other found elsewhere in the solar system. Later, in March of 2022, deeper analysis unveiled that, in the planet's southwestern quadrant, bordering the heart-shaped luminous region, lie immense domed mountains, their surfaces rough and uneven. One, known as Right Mons, towers nearly 3 miles high and sprawls 90 miles across. Its size rivals Hawaii's mighty Mauna Loa volcano on Earth. Not far away, Picard Mons stands as another titanic dome. These are not volcanoes of fire, but of ice. When they erupt, they send forth not molten rock, but a muddy blend of water, ice, methane, and volatile chemicals, creeping out like a glacial slush. What makes Pluto's icy volcanoes so fascinating is their evident youth. The region around them is almost untouched by impact craters, hinting that these cryovolcanoes emerged in the recent geological past. Their age may be just a few 100 million years, or perhaps even less, a fleeting instant on the scale of the cosmos. Some researchers speculate that the area remains geologically active, ever so slowly renewed by the sluggish flow of half-frozen material from Pluto's depths. This unexpected activity is a true puzzle. Pluto's size is modest, measuring just 2/3 the width of Earth's moon, and it orbits far from the sun, so one would expect its inner warmth to be gone by now. Yet these towering ice volcanoes suggest the planet somehow maintains enough energy to drive geology late in its existence. This has forced a profound shift in how scientists perceive dwarf planets, leading to an intriguing question: what hidden warmth still churns within Pluto? Some experts believe the heat arises from radioactive materials locked in Pluto's rocky heart. Others suggest the presence of chemical antifreeze deep inside, compounds like ammonia that lower water's freezing point, allowing it to remain fluid and warm beneath the ice. Regardless of its source, Pluto's cryovolcanoes stand as frigid evidence that this distant world is far from lifeless. During the flyby, New Horizons also recorded huge fissures and sunken areas along Pluto's crust, tectonic scars that point to changes stirring within. It appears the planet's icy exterior has been stretched and torn by forces pushing up from below. Scientists interpret these enormous rifts as signs that a hidden ocean beneath the surface is gradually freezing. As strange as it may seem, Pluto might conceal a vast liquid water ocean lying scores or perhaps even hundreds of miles under its frozen exterior. When water freezes, it grows in volume, much like a bottle bursting in a cold freezer. The slow transformation of a buried sea into ice could force Pluto's surface outward, splitting the crust. Indeed, photographs reveal that Pluto's shell has fractured and shifted over the eons. Yet there is no sign that this secret ocean has ever frozen solid. If it had, the water would become dense, high-pressure ice, known as ice 2, which actually contracts instead of expanding. Ordinarily, such a dramatic global compression would leave behind unmistakable evidence, sections of the crust pressed downward or buckled inward. Yet, New Horizons detected no trace of these telltale distortions. This absence makes researchers wonder whether a hidden reservoir of liquid water still lurks beneath Pluto's frozen surface, as Dr. Alan Stern, principal investigator for New Horizons, suggests. But how could liquid water survive in the planet's deep interior when the temperature at the surface hovers around minus 382 degrees Fahrenheit? Scientists theorize that Pluto's core and mantle have preserved warmth from the time the planet first formed, with insulation serving as a crucial factor. According to a recent study, an insulating layer of gas hydrates, essentially ice combined with gases like methane, may coat the underside of Pluto's icy shell, acting as a protective blanket. These methane-laden clathrate ices conduct heat extremely poorly, slowing the loss of warmth and keeping the ocean underneath from freezing solid. Moreover, ammonia dissolved in Pluto's water helps prevent freezing, functioning like an antifreeze and enabling the briny depths to remain liquid even at incredibly low temperatures. All these clues point to Pluto being an ocean world, albeit one sheathed beneath a thick shell of solid ice. This notion places Pluto among other ocean worlds like Europa and Enceladus, though unlike them, Pluto's hidden sea does not rely on the tidal flexing of a massive parent planet for heat. In fact, research from 2020 proposed that Pluto might have had a fiery beginning. Violent impacts may have generated enough heat to melt the planet's internal ice, forming a liquid ocean early on. If that is true, Pluto's ocean could have existed for more than 4 billion years, a dazzling prospect suggesting that this remote dwarf planet is far more active and perhaps more hospitable than anyone once believed. Above Pluto's icy landscape floats a delicate, translucent atmosphere, a ghostly blue haze composed mostly of nitrogen, tinged with methane. This ethereal layer surprised scientists when New Horizons captured it, glowing blue as the sun rose and set over Pluto. For a time, the atmosphere actually swelled. When Pluto drew closest to the sun around 1989, sunlight warmed the frozen gases on its surface, causing them to sublimate and thickening the atmospheric blanket. Ground-based telescopes recorded that between 1988 and 2016, Pluto's atmospheric pressure nearly tripled as more nitrogen entered the sky. But now, Pluto is journeying away from the sun in its 248-year orbit, and atmospheric pressure is dropping. In 2019, astronomers observed a stellar occultation, Pluto passing in front of a distant star, and discovered that since 2016, the planet's atmospheric pressure had fallen by over 20%. Another occultation in 2018 confirmed that the air is indeed thinning. Pluto's nitrogen is beginning to freeze out, settling as frost back onto the surface. If existing models hold true, this marks the start of Pluto's atmospheric collapse. Dr. Andrew Cole and his team, who have followed the planet's changing seasons through stellar occultations, predict that by the 2030s, Pluto's atmosphere could almost entirely freeze, condensing into a crust of ice. During the prolonged frigid winter, especially after 2030, when the northern hemisphere is plunged into darkness, temperatures will fall so low that any trace of gas will cling to the ground as thick layers of nitrogen and methane ice. For decades, Pluto may become a virtually airless, glittering frozen sphere, its sky empty except for rare wisps of vapor over sunlit patches. This cycle is not eternal doom, however. Centuries from now, as Pluto's southern pole tilts back toward the sun, the ice will begin to sublimate again, and the atmosphere will return. For now, though, we are witnessing an extraordinary phenomenon, the ongoing contraction and potential temporary disappearance of a planetary atmosphere right before our eyes. As pressure wanes, the striking blue haze that New Horizons once photographed will slowly vanish. Curiously, Pluto's overall luminosity might actually rise a little as more of its landscape becomes blanketed with fresh, glistening frost. It is equally astounding that in 2015, as New Horizons soared above Pluto's equatorial band, it caught sight of something wholly unanticipated: dunes. Indeed, formations reminiscent of the wind-sculpted sand dunes found on Earth. These are positioned where Pluto's immense frozen plain borders its encircling mountains. Their existence was validated in a study from 2018 led by Dr. Matt Telfer. The dune-like ridges occupy a zone spanning 46 miles across the western margin of Sputnik Planitia. This is Pluto's prominent heart-shaped nitrogen ice plain at the very junction where it meets the towering Aladrisse Montes, mountains of water ice stretching up to 3 miles high. Here, rows of elevated terrain run in parallel, mirroring the look of wind-driven dunes, though in Pluto's case, the grains composing these ridges are made of solidified methane. But how can such dunes arise with so feeble an atmosphere? The surface pressure on Pluto is a mere 1 pascal, making it about 100,000 times thinner than Earth's own atmosphere. According to prevailing scientific thought, an environment this rarefied should be incapable of lifting or shifting sand grains. Yet, Pluto has managed it. During the course of each solar day, solid nitrogen on Sputnik Planitia can sublimate straight into gas, unleashing energy as it does so. As this gaseous nitrogen expands and ascends, it is capable of momentarily suspending fine particles into the air. Dr. Telfer and his team demonstrated that if methane ice grains, each only a few hundred microns in diameter, are launched by sublimation, Pluto's faint breezes, possibly reaching around 22 miles per hour, can ferry these particles and gather them into distinct dunes. These wind-borne grains most likely originate from frozen methane in neighboring mountains, where methane ice caps endure, though fragments of nitrogen ice may also mingle among them. As the surface of Sputnik Planitia is youthful in geological terms, constantly rejuvenated by flowing nitrogen glaciers, the dunes themselves are probably quite recent, perhaps shaped within the past 500,000 years. The detection of dunes on Pluto reveals the astonishing vitality of this far-flung world. A tenuous atmosphere does not equate to dormancy. Mars, with air also thin by Earth's measure, hosts dunes of frozen carbon dioxide. Even Titan, Saturn's largest moon, boasts dunes formed from hydrocarbons. Now Pluto joins their ranks, illustrating how planetary winds can carve landscapes even under the frigid, low-pressure extremes of the Kuiper Belt. After its historic encounter with Pluto, New Horizons continued its voyage toward an even more remote destination, 486,958 Oricoth, once known as Ultima Thule. On January 1, 2019, the spacecraft swept past this minuscule world at a distance of roughly 4,100,000,000 miles from the Sun, bestowing humanity with its inaugural close-up view of a primordial Kuiper Belt object. New Horizons revealed a body that resembled a cosmic snowman, 2 unevenly shaped lobes fused together. The entire object stretches about 22 miles in length, with one segment measuring nearly 13 miles across and the other close to 9 miles. This is what astronomers term a contact binary, created from the fusion of 2 separate entities. Photographs collected during the flyby display an unexpectedly smooth surface, a uniform reddish tint, and a scarcity of impact craters. In many respects, Oricoth stands as the most untouched and ancient celestial body ever explored, a genuine relic from the very beginnings of our solar system. Among its most notable surface traits are the large mound-like sections forming much of its greater lobe. A recent analysis using high-resolution images uncovered that the larger lobe, nicknamed Wenu, is covered by close to a dozen sweeping mounds, each measuring about 3 miles in diameter. These mounds are strikingly alike in form, scale, hue, and shininess. New Horizons scientist Will Grundy observes that Oricoth almost takes on the appearance of a raspberry fashioned from small, clustered components. The lesser lobe, called Weo, may also possess several of these mounds. Remarkably, Oricoth has remained so well preserved that we are able to directly observe the very building blocks from which it was assembled. These intricate, mosaic-like structures hint at an exceptionally gentle formation method. Experts propose that the mounds are locally generated segments, all stemming from the very same original cloud of cosmic material. They are not remnants from catastrophic impacts. Instead, they are more like siblings, developing side by side before slowly coalescing into a single body. An abundance of evidence backs up this idea. considering both the form and the chemical signature of Oricoth. The two lobes meet precisely at a junction, with their poles and equators in harmony, implying that they once circled each other and gradually drew closer in a slow spiral. Each lobe is noticeably flattened, echoing the shape of a pancake, which likely results from a calm convergence within a whirling disk of debris. Of particular interest, both lobes display an exceptionally consistent color and chemical makeup across their surfaces. This uniformity suggests the material that built this object was drawn from a single, localized sector of the solar nebula. Had Oricoth developed through the classic path of hierarchical accretion, random collisions assembling matter from widely scattered places, we would see far more diversity across its surface. Yet, every piece of evidence favors a different birth story, the cloud collapse scenario. In this model, a dense cluster of solid particles within the ancient solar nebula succumbed to its own gravity and directly compressed into a planetesimal, skipping the stage of chaotic collisions. As co-author Dr. William McKinnon explains, Oricoth's particles formed in close proximity, moving slowly, orbiting one another in an elegant gravitational ballet until they eventually fused. All available data supports the particle cloud collapse model, effectively ruling out hierarchical accretion for Oricoth's origins. This revelation is a critical clue in unraveling the age-old puzzle of how planetesimals, the seeds of planets, came to be. Curiously, the faint reddish tint of Oricoth's exterior is not a trivial detail. It provides a glimpse into the chemistry of the early solar system. Observations from the New Horizons spacecraft revealed that Oricoth's surface is sheathed in methanol ice and complex organic substances, probably tholins, which will be discussed soon. Astonishingly, no water ice was found on its surface. This is unexpected because water ice is widespread among other distant solar system bodies. Comets and Kuiper belt objects, even the smallest ones, often reveal water's presence. The absence here hints that either water is hidden beneath organic layers, or the conditions during Oricoth's formation led to a remarkably dry composition. Instead, Oricoth is classified among the ultra-red objects, its reflective spectrum intensely red because of an abundance of surface organics. Scientists believe this reddish coating is rich in tholins, which are complex molecules created when cosmic rays and ultraviolet light strike simpler substances like methane, ammonia, and nitrogen. Though tholins are not living, they are prebiotic, containing many chemical ingredients that, under certain circumstances, can give rise to amino acids and other building blocks of life. The detection of frozen methanol offers an additional clue about Oricoth's past. Methanol may form by irradiating water and carbon monoxide, or it may be a primordial ice. It is less volatile than gases such as methane or nitrogen. Researchers believe that more volatile ices, like methane, ammonia, and hydrogen sulfide, were likely present on youthful Oricoth. But with gravity so feeble and the surface so frigid, over billions of years, these substances either dissipated into space or changed chemically. The discovery of sulfur-rich tholins suggests that compounds such as hydrogen sulfide once contributed to the surface chemistry. As these gases escaped or transformed into solid polymers, what was left behind was a reddish organic frost and a layer of methanol ice, a sort of organic glaze that now coats Oricoth's surface. The striking lack of water ice on the surface could suggest that it lies hidden below a thick layer of organic material, or it may hint that in Oricoth's sector of the solar nebula, the temperature dropped so low that water ice merged into larger entities, leaving this planetesimal to form mainly from carbon-laden ice and dust. Either way, its makeup reveals that the building blocks for planets were far from uniform. By examining these ingredients up close, we gain a window into the chemistry of the outer solar system as it was 4.5 billion years ago. These very substances might have made their way to Earth carried by comets and asteroids, possibly sowing the seeds for the origins of life's ingredients. Essentially, this dead world has locked away the organic chemistry from the earliest days of the sun, preserving it like a time capsule, an initial toolkit for life's recipe. Naturally, this led to a tantalizing question. Could life exist within Pluto's concealed ocean? If Pluto has sustained a liquid ocean beneath its crust for billions of years, then it offers a stable aquatic environment, which is fundamental to every known living organism. That ocean is likely rich in ammonia and salts, which not only prevent freezing, but may also double as nutrients. If the core of the dwarf planet generates thermal and chemical gradients, it could supply energy sources akin to hydrothermal vents on Earth's ocean floor. To be clear, there is no proof of life on Pluto. The New Horizons spacecraft was not equipped to detect biosignatures. Yet the mere possibility of a hidden sea so far from the sun suggests that Pluto may be more hospitable than once imagined. In the words of one expert, any living things beneath Pluto's frozen surface would be well protected from relentless cosmic rays and insulated against wild temperature fluctuations. Such organisms would most probably be microscopic chemoautotrophs, drawing energy from chemical reactions between rock and water. Although this scenario is not likely, it remains an open question. Did tiny life forms ever emerge in that secret ocean, or could they still appear in the present day? We may not have an answer until a future probe ventures into those dark, submerged depths. New Horizons gave us only fleeting glimpses, just a handful of days to study Pluto, and mere hours for Oricoth, but those short visits transformed our knowledge. Even now, years later, planetary scientists continue to analyze the mission's data, unveiling fresh discoveries. Yet, numerous puzzles endure, and some are only now beginning to reveal their secrets. Did Pluto erupt with icy volcanoes in the not-so-distant past, and is this activity ongoing? How does the climate of this dwarf planet shift as its thin atmosphere wanes and then regenerates? Is the hidden ocean touching the rocky core, or is it locked away beneath a barrier of hydrates? How deep is the icy crust, and might there be pockets of liquid water closer to the surface? Are all frigid, classical Kuiper Belt objects similar to this, or is Oricoth an exception? Solving these mysteries will demand bold new missions and creative strategies. Excitement is growing among researchers for another journey to Pluto. For example, NASA has begun funding early studies into an orbiter that would not simply zip by, but would linger to investigate Pluto and its moons for many years. The plan involves a spacecraft arriving at Pluto, settling into orbit, and mapping the dwarf planet in exquisite detail, tracking seasonal shifts in its atmosphere, and perhaps even dispatching a lander or impactor to study its surface close up. Because entering orbit calls for a great reduction in speed, advanced propulsion systems are being considered. These include ultra-efficient ion drives powered by nuclear generators, or even visionary options like thermonuclear propulsion. One particularly ingenious proposal is to use Pluto's largest moon, Charon, as a gravitational slingshot to help slow the spacecraft. Scientists have determined that the orbiter might utilize multiple gravity assists around Charon, allowing it to decelerate or even break free from Pluto's orbit while consuming only a small amount of fuel. This maneuver would permit an extensive exploration of the entire system, followed by a journey toward additional Kuiper Belt objects. One suggested mission outline envisions the spacecraft spending 2 full years encircling Pluto, then harnessing Charon's gravitational pull to depart and travel onward to visit at least one more Kuiper Belt object, possibly one of the cold classical bodies, and maybe even to sweep past another dwarf planet. If achieved, this bold endeavor would dramatically broaden the legacy of New Horizons, converting what began as a brief reconnaissance into an enduring adventure. While plans for future exploration are being crafted, New Horizons itself remains hard at work. The probe has pressed on past Earth, collecting data from the Kuiper Belt and within the heliosphere, the vast zone molded by the solar wind, while also surveying distant worlds, recording dust and energetic particles, and scouting for further promising targets for flybys. NASA has approved the continuation of New Horizons at least until the latter part of the 2020s. This means the spacecraft will likely keep sending updates from the outskirts of the Sun's domain, and may even push far enough to reach the cosmic frontier where interstellar space begins. Pluto and Oricoth have revealed that the outermost parts of our solar system are not simply frozen wastelands, but regions alive with shifting geology, evolving atmospheres, and preserved records of the past. As new missions gear up for launch, we wait, not for some far-off fantasy, but for the next breakthrough, which is already beginning to unfold.